Is it okay now? Somebody complained about some noise.
Yes, ma'am. Now it is okay.
Okay. Alright. So recording is in progress. I'll share my screen. Is my screen visible?
Yes, ma'am.
Yes.
Okay. So we're going to start discussing the questions. So this is the question we have. Let A be a 3 by 3 matrix with determinant 3. Which of the following operation transform A to matrix B with determinant -6? Choose all the correct options. So would anyone like to attempt? Right. So let's break down the problem. So what is being asked here is that we have been given a matrix A and its determinant is given as 3. And A is a 3 by 3 matrix. Okay. Now we are applying transformation operation to transform. So basically what we are doing is we are applying row operations, right? So we are transforming A to B using row operation. And what row operation are we applying? So the question is about the operations and how those operations are going to affect the determinant and change the determinant. So the row operation will be applied in such a way that it yes somebody replied the answer is A and C. Yes, that's the correct answer. So let me just briefly explain how this is happening. The row operation is being applied and it is affecting the determinant will change from 3 to -6. So we have to identify which row operations do that. So we know that when we interchange the row, then the determinant gets multiplied by a negative. Okay. So in the first option, multiply the first row of A with 2. So when we multiply some row, like so if this is A and the A has row 1, row 2, row 3, okay, and this gets changed to 2, row 1, row 2, row 3, okay. Then what is happening? Then we are interchanging the third row and second row. So further row operation is, so this becomes like this. So how does that change the determinant? So the determinant, so this row exchange, due to this the determinant becomes negative, and this multiplication, due to this the determinant gets multiplied by 2. So determinants become -2 into determinant of A, which is -2 into 3, which is -6, and hence this is the correct option. Then matrix is multiplied by -2. So when the matrix is multiplied by -2, then all the rows are getting multiplied by -2, which means -2 raised to the power 3 into A. That becomes the determinant in case of option 2. Okay, in case of option 2. Which is not what we want. We want -6. So this is not the correct option. Now add third row to the first row. So when we add two rows, the linear combination, we are going to cover questions that will cover almost all the weeks. Okay. We are not going to go over the theory because I believe that you must have gone through the theory on your own. So we are going to go through the questions, and through the questions we are going to cover most of the weeks. Right. So addition of row does not change the determinant, but after that we are multiplying the second row by -2, and hence -2 into determinant of A, which is -2 into 3, which is -6, and hence we have third option as the right answer. Interchange the first and second row. Interchanging the row means the determinant gets multiplied by a -1, and then we multiply the third row by -2. So in case of the third option, sorry, last option, in case of the last option, the determinant of B dash is -1 into, we are multiplying by -2 into determinant of A. So that is 2 into 3, which is +6. We want -6. Okay. So that's why not the correct answer. The correct answer is A and C. Um, Now we are going to go to the next question. The next question is, assume the usual vector addition and scalar multiplication for all the options below. Choose the correct option from the following statements. Okay. So we have to, on the basis of usual vector addition and scalar multiplication. So what is usual vector addition and scalar multiplication? Okay. So this we'll see this with the first option. Usual means like for the case of when we have xy belongs to R2, then vector addition will be defined as component wise addition, and right. So C is a scalar, and this is the usual vector addition and scalar multiplication when xy belongs to R2, right? So the first option is given that the set of vectors xy belongs to R2 such that x plus y is equal to 1 forms a vector space. Now remember that in the definition of vector space, the vector space must have what must it have? It must have a zero vector, right? It must have a zero vector. So when we have x plus y is equal to 1, so if this is x-axis, this is y-axis, x plus y is equal to 1 passes through the point 0, 1 and uh, 1, 0, right? So this is a line like this, and clearly we can see that this does not pass through the origin. So this means that this line does not contain the 0, 0 point, which is the it does not belong to this particular set which is given to us in option A, and hence this is not a vector space, so this is false. Okay, this is the not the right option. Now what is the next one? The next one says that Yes, the session is getting recorded. Okay. So the next one says that um, let A be a 3 by 3 matrix. Okay, wait, I need to. Uh, right. So, let A be a 3 by 3 matrix such that the columns of A are linearly independent. Right? So, when we say we are looking at the second option, A is a 3 by 3 matrix and columns are linearly independent. So, when columns are linearly independent, um, you can get the recording after the session. Okay. Um, well, how can I send you recording link before the session gets recorded? So after the session you can get it, right? Um, okay, so I'll continue. So let A be a 3 by 3 matrix such that the columns are linearly independent. So the columns are linearly independent, which means that A is invertible, right? Determinant of A is non-zero. A inverse exists. Now, the set of all solutions of homogeneous system Ax is equal to 0 is a vector space of dimension 0. So we have to say whether this statement is true or false. The set of all solutions of the homogeneous system Ax equal to 0 is a vector space of dimension 0. So Ax is equal to 0. What does it mean? It means that we have an invertible matrix and at the we are looking at the set of all solutions of the system Ax equal to 0. The set of all solutions of the system Ax equal to 0 means the null space of A, right? This is we are talking about the null space of A. And what are we saying? We are saying that the null space of A is a vector space of dimension 0. Now, the columns of A are linearly independent, which means that rank of A is 3. Why 3? Because A is a 3 by 3 matrix. So rank of A is 3. And we want to find what the dimension of null space. What is the dimension of null space? We know from rank nullity theorem that the dimension is, right?
Yes,
Right?
ma'am. Yes, ma'am.
Right? So 3 equal to 3 minus 0. So dimension of the null space is what? Dimension
Zero.
of the null space is 0. Okay. So the second option is correct. The set of all solutions of Ax equal to 0 is a vector space of dimension 0. Now, the next is the set of all n by n matrices with rank strictly less than n does not form a vector space. Does not form a vector space. Okay, it's not saying it forms a vector space, it's saying it does not form a vector space. So, uh, consider, okay, what does it say? Right. So, consider two matrices. Say, for example, 1 0 0 0. Okay, and another matrix 0 0 0 1. Now the rank of A is 1 and rank of B is also 1, right? It is saying that this does it rank strictly less than n does not form a vector space, right? So what happens when we add A and B? we get 1 0 0 1. Okay, and the rank of this particular matrix is 2, right? If it formed vector space, then rank will be like less than or equal to 1, like, is that what they're saying? Yeah, it should be strictly less than n, so it should be strictly less than 2. Rank should be strictly less than 2 if it formed vector space, but we are getting that the rank is 2, which means it does not form vector space. So if it does not form vector space, then the statement that is given here is correct. Okay. Now moving to the next statement. The next statement says that the set of all n by n matrices with determinant 0 forms a vector space. Let's read the statement again. It says that the set of all n by n matrices such that determinant is 0, it forms a vector space. So we have to check whether it forms a vector space or not, right? So let's take an example and see. For example, let's take a matrix 1 minus 1 1 minus 1. See that the determinant of this particular matrix is 0, right? Minus 1 plus 1, the determinant is 0. So let's take another matrix whose determinant is 0, and we are going to add the both matrices. Okay, so the second matrix is again 2 6 1 3. So you can see 6 minus 6 0, determinant is 0. Why are we going to add it? To check vector space, we have to check two conditions. Option 3, which option 3? This particular option 3, where we are checking the rank.
Yes, ma'am.
Right, okay. Okay, so look at the option. The set of all n by n matrices with rank strictly less than n does not form a vector space. So for n by n matrices, we can take any n by n. So in the particular example that I showed here, I took a 2 by 2 case, right? So for 2 by 2 case, I considered two different matrices, and I have to show, like, for showing vector space, two major conditions have to be checked. Which conditions? That if we take any two vectors from a vector space and add those two vectors, then the resultant vector should also lie in that vector space, right? And so what we did, we took two matrices with rank strictly less than n. We had taken 2 by 2 matrices, and for 2 by 2 matrices, each had rank 1. So 1 is less than 2, right?
Right?
So 1 is strictly less than 2. uh, and hence when we are adding the two matrices, we are not getting rank strictly less than 2, we are getting rank 2, which means if it were a vector space, then the rank should come strictly less than 2, it should belong to the vector space, but it does not belong to the vector space. The sum a plus b lies outside, so this is not a vector space. And the statement was asking if it is not a vector space, it's not asking, it does not, see, it's asking if it is not a vector space, and hence this is the correct statement because we showed that it is not a vector space. Yeah, is it clear? All right, so moving on to the next option, the set of all n by n matrices with determinant 0 forms a vector space. Similarly, to show something is a vector space, we have to take, yes, the addition rule fails. Yes, in the last option also we show that the addition rule fails. We have taken two matrices for the 2 by 2 case. We have taken 2 by 2 case, we can take 3 by 3 case, any n by n case we can take, right? So here when we add them, we get 3 5 2 2, and the determinant is clearly not 0. Yeah, 6 minus 10 minus 4. This is the determinant of, say, S. This is S. So determinant of S is not equal to 0, which means that this particular case does not form a vector space, and hence this last option fails and it is not the solution. Okay, right. So moving on, consider subspace W is a 2 by 2 matrix ABCD where A plus B is equal to C and C plus D is equal to B minus A. Okay, so we have to find the dimension of W. So if we break down W, yeah, I hope I have, okay, and we have A plus B is equal to C and C plus D is equal to B minus A, right? So what does it mean? It means that A, B and C is A plus B, and what is D then? A plus B plus D is equal to B minus A. B gets cancelled, so D is minus 2A, and we put it here, right? And when we apply row operation to it, uh, this is straightforward, so I'm not really explaining the row operation. You can see the calculation how it is being carried out, right? And this becomes minus 2A minus B minus B by A into B. Okay, something. So this is also non-zero. So some non-zero number here, some non-zero number here, which means that dimension of W is equal to 2 because the rank of W is coming as 2. Okay. Uh, so now we move on to the next question. Okay, this is the similar one. I think you can do it. This is similar type of question that we had seen. So do I need to explain this or the current question? So okay, fine. I'll explain it again. So let A by A be and 4 by 4 matrix, and determinant of A is minus 2. Which of the following? So some row operation, some operation transforms A to B such that determinant of B is 10, which means that this particular transformation, the result of this particular transformation is that the determinant of minus 2 gets multiplied by minus 5. Okay, so let's see which operation. So multiply the matrix A by minus 5 will not be the case. Why? Because for each row, so if you have a matrix A, 3 rows A, okay, and we multiply A by minus 5, then this becomes minus 5 R1, minus 5 R2, minus 5 R3. So the determinant of minus 5A becomes minus 5 cube into determinant of A, because each multiplication with each row results in a multiplication of minus 5 with the determinant, which is why this is minus 5 cube determinant of A. And so the second option is not correct. uh, First option is add second row to fourth row and multiply second row with minus 5. This is the correct option, because we are only multiplying one row with minus 5, and addition of two rows makes no effect on the determinant. Now interchange the first and third row. Interchange means when you interchange, determinant gets multiplied by -1. Okay, so interchange results in multiplication of -1 with the determinant, and multiply fourth row with 5. So ultimately we are multiplying determinant of A with -5, and so the third option is correct. What is the fourth option? The fourth option is multiply second row with 5, right? And then multiply the third row with -1. This also results in multiplication of -5 with the determinant. So this is also the correct option. Three correct option in this particular question. Uh, okay. So now we go to the next question. Okay. So this is an interesting question. So let f be a scalar valued multivariable function. So when we say scalar valued, so f is a function from D to R. Scalar valued means it is real valued function. The function is going to R, and D is a subset of R2, right? It is given here, D is a subset of R2. So scalar valued multivariable. Multivariable means f is of this form. It's taking the value from R2, because D is a subset of R2. So from here it is giving some scalar value. Okay, so choose all the correct statements from the following statements regarding the directional derivative fu of f in the direction of unit vector u, right? Directional derivative fu of f in the direction of unit vector u, right? So what is the first option? The first option is that if the partial derivative of f exists at point AB, then FUAB means directional derivative of f in the direction of unit vector u at the point AB. So this FUAB exists for all unit vectors u. We have to say whether this is true or whether this is false. Um, right, so let's look at a function. So consider the function fxy is equal to xy divided by x square plus y square, where xy is not equal to 0 0 and 0 when xy is equal to 0 0. Okay, let's consider this particular function. Now we said that partial derivatives of f exist at point AB. So let's take the point AB as 0 0 in this case. Okay, so in our example we are taking AB as we are taking this as, this is not given. We are taking AB as 0 0, and we are going to find the partial derivative, right? So how do you find partial derivative? So partial derivative of x at point xy by definition is given as limit h tends to 0 f of x plus hy minus fxy divided by h. So what does it mean? It means y remains same, we are taking partial derivative with respect to x. With respect to x means that small change in value of x. We are only changing small change in value of x, and we are taking its difference with fxy, and we are finding the limit in that particular point, the xy. Okay. So if we take fx00 of the particular function that I have taken in the example, um, so we are going to calculate this. So before that, see that fx0. So if I put the value of y as 0 in fxy, then I have 0 divided by x square, which is 0, right? So del f uh, one sec, I'll take it in the next page. So del x at 0 0 will be limit h tends to 0. This is coming as 0, and this is given as 0. So this becomes 0 minus 0 divided by h is equal to 0. Similarly, del f del y 0 0, this also comes out as 0, right? So the partial derivative exists at 0 0. Now we have to check whether the directional derivative exists or not. fu00, does it exist? Um, so fu00 will be limit h tends to 0 f. So what is u here? What am I taking u here? What is u?
Unit vector.
Yes. Yes, the unit vector. And since this is the example I'm taking, so I'm taking u as cos theta sin theta. Okay. I'm trying to see if the directional derivative exists in this particular direction. Okay. So limit h tends to 0, fx, here x0 is 0, so 0 plus h, this is u1, this is u2, so u cos theta, 0 plus h sin theta. I'm first writing the formula. Minus f00 divided by h. Okay, this is basically what I did. I wrote the formula for directional derivative at point uh, 0 0 in the direction u. So by applying the formula, you are going to get this. Okay. So what is this? This is given as 0. The example that I took here, this is given as 0. Why did I take the example? I am trying to evaluate whether the given statement is true or not. So when you have to evaluate when a statement is true or not, it is usually helpful to take an example and evaluate and see whether it is satisfying the condition or not. So limit h tends to 0, f of h cos theta, h sin theta. Now this is 0, so I'm not writing it. Divided by h. So what will this come as? So x I have taken as h cos theta and y I have taken as h sin theta. So this becomes, the numerator becomes h square sin theta cos theta. Denominator is h, and what is the this is x square plus y square, so h square sin h square cos square theta plus h square sin square theta. So we know that sin square theta plus cos square theta is equal to 1, and this come as h square, right? So this is what? This is limit h tends to 0. For that function, put y equal to... no, the limit will not exist. Sin theta cos theta divided by h. So you see that this is 1 by h. So as h tends to 0, the function tends to infinity. So this is not defined. So what did we see? We saw that the partial derivative exists, but directional derivative does not exist, right? What was the statement? The statement was, if partial derivative exists, then directional derivative also exists. But we have shown for a particular function that the partial derivative exists, but directional derivative does not exist. What direction we took? We took the direction cos theta sin theta, and so this particular option is incorrect. Now the second one. So if fu exists at point AB for all unit vectors u, then partial derivatives of x of f exist at AB, right? So if fu exists at point, fu is what? Directional derivative of f in the direction u at a point AB. So we are saying that directional derivative exists for all unit vectors, means it exists in all directions, then partial derivative exists. Yes, this will be true. This will be true, but partial derivative exists does not mean that the function will be differentiable, right? So this will be true, and I'm going to show it using one example as well. Consider this particular function. I'm sorry. Right. So now let's take just any random unit vector you can take, not just this. Why? Because we have considered one example where directional derivative exists in all direction, right? So when you solve it, you'll get something like this. So if I'm going to see here, what did we do? 0 plus h 0 plus u1, 0 plus u2 minus f 0 0 divided by h. So I'm going to apply this particular formula only. Because why? Because this is 0 0. So this is 0 again in this particular example. And you can solve it and see that this is coming as like you just have to put the value here. Where is the example? Yeah, this is the example. Just put the value of u1 and u2 for x and y and solve it, and you're going to see that the directional derivative is going to exist. And if you're going to take partial derivative, so say first you put x cube by x square plus y square, right? So this is the fxy is x cube by x square plus y square. So if you put the value y is equal to 0 in this particular function, then you get fx0 as x. So del f del x at 0 0 is going to be 1, right? And if you put x as 0, then you get here 0, and del f del y at 0 0 is going to be 0. So what did we see? We saw that directional derivative exist when a function is there where directional derivative of that function exists in any particular direction, then its partial derivative also exists. Okay, this is just showed by example. Okay, now the third one. The third one is that gradient of x exists at point AB. Del f is gradient of f. What is gradient of f? For finding the gradient, we need to see that partial derivative exists, right? So if partial derivative exists, then gradient exists. So if gradient exists at point AB, then tangent plane to the graph of f exists at that point. So we have to check if the tangent plane exists or not, given that gradient of f exists at that point. So option C. Um, so what is the tangent plane? So if we have a surface z is equal to fxy, and say we have a point p0 in 3 dimension, then the equation for the tangent plane to s at p0 is z minus z0 is equal to fx x0 y0 x minus x0. This is the formula. I'm writing the formula for tangent plane. Right? So if the equation is written in the form ax plus by plus cz plus d is equal to 0, this is a plane, right? So plane equation, so line equation has 2 parameters x and y, plane equation has 3 parameters x, y and z. This is not a subscript, this is c into z. Okay, so here where z can be derived from this particular equation. Now we are saying that the gradient of this exists. Now gradient exists means partial derivative exists, but look at the first option where we saw using an example that when partial derivative exists then directional derivative may not exist. So when gradient exists, partial derivative exists, but when partial derivative exists, directional derivative may not exist. And look at the equation for tangent plane. We need directional derivative here we need directional derivative. So what does it mean? It means that this partial derivative exists, but directional derivative may not exist. So if directional derivative does not exist, then we can't find this particular plane. We can't find z and we can't find this plane. And if we can't find this plane, then the tangent plane also may not exist for the case of directional derivative not existing, right? And so the third option is false because tangent plane to the graph may not exist. Okay, now coming to the fourth option. Um, the fourth option is if there exists a point AB belong to D such that gradient of f at AB is equal to 0 and del f is continuous in a neighborhood around AB, then we are finding fu equal to 0. Fu means directional derivative of f in the direction of unit vector u. So let's break the last option down. It says that del f ab is equal to 0 0 and del f is continuous near AB. Okay. Uh, so if the directional derivative at the point exists and if it continuous near that point, then it means that f is differentiable there. Okay, f is differentiable there. So if f is differentiable there, then directional derivative will exist. So FUAB can be written as, we can use the gradient formula here, multiply the dot product of gradient with the unit vector, that is given as 0. This is given as 0 and so the result will be 0. So the last option is correct, right? Okay. So now we go to the next problem. So consider the function f from R2 to R defined as fxy is equal to x minus y whole square sine 1 by y for x not equal to y and 0 when x equal to y. So we have to say which of the following statements are correct. The function f is continuous at 0 0. So we have fxy is equal to x minus y whole square sine 1 by y for by x minus y. This is for x not equal to y, and 0 for x equal to y. And we have to check the continuity. So, okay, say take x minus y is equal to h, right? So why did we do that? What is we basically, what did we want to do? We wanted to take uh, for putting the value in the formula for continuity, we have to take limit for a small change, right? So here we are taking x minus y equal to h because we are going to take the small change and we are going to see it for the case of x minus y is equal to h. And when that happens, then what is the value of f? The value of f is h square sine 1 by h, right? And limit h tends to 0. So notice that as h becomes smaller, so this is a bounded function because the value of sine is always between minus 1 and 1, and this is going to 0. H tends to 0 means h square also tends to 0. So we are getting the limit as 0. When the limit is 0, so as x y tends to 0 0, fxy tends to 0, and f of xy is equal to 0 when x is equal to y. That is, f of 0 0 is equal to 0. Hence, we are getting the value of limit and the value of function as same, which implies that the function is continuous at 0 0. We have to check for 0 0. So whenever the value of the limit evaluates as equal to the value of the function, so the limit is coming as 0 and value of the function at this point is also 0. So the function is continuous at this point. This is true only for this point. We have to check for other points, but we don't, like, the question is asking only for this point. So we have to bother only about this point. So this is coming as continuous at 0 0. Uh, so this is continuous. Now the next one, there is a direction along which directional derivative of f does not exist at 0 0. So is there a direction? Is there a unit vector along which direction the directional derivative of f does not exist? At which point? At 0 0. So um, let's take x equal to y to be that direction, right? So, and the point is given as 0 0. So if we take fx0, then we have x square sine 1 by x, right? Why? Because we have taken y is equal to 0 for the purpose of finding directional derivative. So for finding directional derivative, we have to first see if the partial derivative exists or not. Now the partial derivative itself will not exist because this is going to oscillate. that was not the case here. Why that was not the case here? Because here h was tending to 0. When h was tending to 0, then the whole function tends to 0. But in this case, we are finding the partial derivative. So in that case, this is oscillating, and so this function does not converge for all direction, right? So the directional derivative will not exist, and they are asking if it does not exist, so hence this is the correct option. Okay, now we are talking about the tangent hyperplane. So we just saw that for tangent hyperplane the directional derivative is supposed to exist, but directional derivative itself is not existing, so equation of tangent hyperplane we cannot find it. So this is the wrong option, because it is like equation of tangent hyperplane of graph f at point z equal to 0. When the tangent hyperplane is not existing, we can't say the equation for it, right? Next we are saying that the vector is orthogonal to, again tangent hyperplane is not there, so there is no meaning in trying to find if it is orthogonal to something or not. So again this is the wrong option. Okay, now okay, so now we are at the next question. So we have a matrix 2 minus 1 1, k minus 2 2, 5 1 6, and k is a real number, and we have to find the value of k for which the system Ax equal to 0 has infinitely many solutions, right? So notice the first two rows of A, right? Notice the first two rows, this and this. This is 2 minus 1 1, k minus 2 2, right? So for infinitely many solution, one of like one of the row will come out as a linear combination of some row. So this is already minus 2 into sorry, this is already 2 into minus 1, and this is already 2 into 1. So if we take k as 2 into 2, that is 4, then what will be our matrix? Our matrix will be 2 minus 1 1, 4 minus 2 2, 5 1 6, and when we apply some row operation like r2 minus 2 r1, then it will become 2 minus 1 1 0 0 0 5 1 6, right? And when we get a matrix of a form like this, then infinitely many solution will exist. So what will the value of k for which infinitely many solution exist? K equal to 4. uh, right, now let's look at the next question. So okay, so the next question gives us as k equal to 3. If k equal to 3, then a becomes 2 minus 1 1, 3 minus 2 2, 5 1 6. Next we have the column B as 1 alpha minus 1. So if we write it like this, okay. Now we have to say which of the following option is true. So if alpha is equal to 2, then the system Ax equal to 0 will have a unique solution. So let's check for that. So let's take. Oh, it's not getting erased for some reason. Anyway, I'll just cancel it and write it. What is the value of alpha? The value of alpha is 2. Okay, so we will apply row operation to it. We have to check for unique solution, right? So if we get unique solution, then this is true. We have other values of alpha as well. Alpha equal to 1, alpha equal to minus 3, and that is to check for different things in different options. But let's do this first. Um, so what are we going to do? R2 minus 3 by 2 R1, and we are going to apply on R3 minus 5 by 2 R1. Okay, so what are we getting? Why are we doing this? What do we want to do? Why are we applying elementary row operations here? We are applying elementary row operations here so that in what condition are we going to get unique solution? So if the rank of this matrix comes out as 3, right? So how will it appear? Some non-zero entry here in the diagonal, and here it can be anything. These 3 entry have to be non-zero. So if the rank is 3 and the augmented side can be anything, then it will have unique solution. So I think I can leave the calculation to you. All you have to do is you have to apply elementary row operation on this matrix and see if this particular part gets rank 3. If you get rank 3, then you get unique solution, and if not, then you will not. So since I've done this before, so you'll get unique solution. You can check using calculation here. uh, we have to cover other questions also, that's why I'm leaving the calculation to you. Okay, so what is the next one? The next one says that infinitely many solution. For what? For alpha is equal to 1, infinitely many solution, right? um the value of k is the same one.
Ma'am, value of k is 1, right? Like they said if k is 1, then it should have infinitely many solutions for the second option.
K is 3.
In the second option, like if alpha is 1, then I should have infinitely many solutions.
Yeah, alpha is in B.
Okay, I'm sorry, ma'am.
Okay, alpha is in B and k is from here, right? The matrix A, we had a unknown entry in matrix A. This was k, and here we were given k as 3, and we have k already, and for B alpha is equal to 1, and we have to check, right? Okay,
Yes,
I
ma'am.
hope this is clear. Hmm? Right, so alpha is equal to 1, and how will you check if this has infinitely many solution or not? What condition are you checking? Can anyone say?
Any one row should contain 0, 0, 0, 0 entry.
Yes, correct. So if any of the row contains 000 entry, all the like all four entries in any row, all four entries in any row, if it is all zero, then the system will have infinitely many solution. And if here we have non-zero, that is in the augmented column, if we have non-zero while here we have zero, then that will be inconsistent and that would mean no solution. So we have to check for infinitely many solution, which means this is not the condition we are checking. What we are checking? We are checking if all the rows are coming as zero or not, right? Okay, so that's what we have to check. uh, so the next one is alpha is equal to minus 3. So we have alpha here, and then the rank of augmented matrix is not equal to rank of A. Okay, we can calculate the rank of this, so this will be clear. What 516, and if we apply row operation, r2 minus 3 by 2, r3 minus 5 by 2, r1. Okay, then yeah, then we have 2 minus 1 1, this is 0. Okay, then we have minus 2 minus 3 by 2 into minus 1, which is plus 3 by 2. So this becomes minus 4 plus 3 by 2, which is minus half, right? Then so I'm calculating the rank of this matrix. 2 minus 3 by 2 into 1, which is 4 minus 3, which is half. Okay, next is 1 minus 5 by 2 into minus 1. So this is 7 by 2. Then this becomes 6 minus 5 by 2.
Ma'am, we have taken the same matrix now, so we will get same rank. Why we are checking?
Yeah, I did not calculate it here. The rank will
Okay,
come out as 3. I'm showing it that it will come out as 3.
okay.
Hmm? Right. So, yeah. 6 minus 5 by 2. This will come out as 12 minus 5 by 2, which is 7 by 2, right? Yeah. Okay. Hmm. So the rank is 2. Sorry, 3. Yeah. And what is here? What is given here? Alpha is equal to minus 3. Rank of the augmented matrix is not equal to the rank of A. So if the rank of A is 3, the rank of augmented matrix will also come out as 3. Right?
Yes, ma'am.
Right. Right. So the this option is correct. This option will come out as wrong, by the way. You can calculate and check. Uh, then alpha is equal to 1. Then B does not belong to the column space of A. What is B? B is 1 alpha minus 1. So 1 alpha minus 1 was 1 minus 1, right? So if we have 1 1 minus 1, and we applied the same operation here, these two operation I'm going to apply to this column. This will basically be augmented matrix for this particular case. So I'm going to apply only to this column because I've already done it for the total matrix, right? So R2 is 1 minus 3 by 2, which is what? which is minus half, and minus 1 minus 5 by 2, which is minus 7 by 2. Correct? So this will come out as 2 minus 1, 1, minus half, half. Okay. What did we want? That B does not belong to column space of A. Does B belong to column space of A? It does not. See?
No, ma'am.
Notice this column and this column. Okay. This has got positive 1, but this is half, this is minus half, this is 7 by 2, this is minus 7 by 2. And if we compare with this particular column, then here we have minus half, this matches, but the other two components do not match. So it does, this B does not belong to the column space of the matrix A. So our last option is correct, because we have to say it does not belong. Okay?
Ma'am,
Yeah.
option 3, in the workout that we did, we got rank of A is equal to the augmented matrix of rank of B, right? Which we got as 3.
Sorry, I did not get your question.
In the workout of option C,
Yeah.
we got the rank of A as 3, right?
Right.
And we said that the rank of the augmented matrix is also will be equal
Oh
to
yeah,
3.
not equal. Yeah, it will be equal. Sorry. Yeah.
So option,
Oh,
okay,
yeah. This
fine.
this option is incorrect. Thank you. Yeah. So we did the correct workout, but we misread the question. This happens in exam also. So you have to be careful while attempting questions in exam. Right. Okay. So now we have matrix A. This is another question, the new question for which subsequent question related question we have to answer. So matrix A, minus 2k 1 3 k minus 1 0, and the first option says that there are infinitely many values of k for which the rows of A span are 2. Right?
Yes, true.
True.
Because we
Yes.
will have a
True, ma'am.
independent variable.
Correct. It will be true. So notice that minus 2k 1 3. So when does it have like infinitely many values of k for which? Okay. So when do the row become linearly dependent? Linearly dependent it would become if k has the value 6, right? Right. So if the k has value 6, then minus 2 6 will be linear combination of 1 3. Hmm? So the option will be true. Next one says that there exists k belongs to R such that rank of A is 1. What was A? A was minus 2k 1 3 k minus 1 0. Yeah. Okay. Yeah. Anyone wants to attempt this? Okay. So there exists k belongs to R such that rank of k is 1. So notice that there are two columns, right? There are two columns, and no matter what value of k we take, the rank of A is always 2, right? because it depends on this value and this value. These two are non-zero values. So you can okay, wait. You can take any value of k, and when you take any value of k, say you take here k equal to 3 also, right? So if you take k equal to 3, then this becomes what does the matrix becomes? K 1 3 1 3 3 minus 1. So if this is 2, this is 0, right? So if you apply elementary row operation, why did I take k equal to 3? I wanted to show that other than 3, so rank will be 2, right? But if I'm going to eliminate this value, even then the rank will come out as 2. 1 minus 2, this is 3, and we add this, right? The rank comes out as 2 again, right? So there does not exist any k belongs to R such that rank is 1. Rank will always come out as 2, so this is false. Right, so the next is when k is equal to 1. When k is equal to 1. So when k is equal to 1, the matrix A becomes minus 2, 1, 1, 3, 0, 0. Okay. Then the column vector span the xy plane in R3. Right?
Yes,
So,
ma'am.
yeah, so because the rank is clearly 2, so you can write this as linear combination of 1, 0, 0 and something and 0, 1, 0. So this component does not change anything because we have non-negative values in these two positions. So this particular this spans the xy plane. Right. Now moving on to the next question. So let T from R3 to R3 be a linear transformation, and A is equal to 2, 3 minus 1, 1, 0 minus 1, 1, 3, 0 is the matrix representation of T with respect to the standard ordered basis. Standard ordered basis is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the standard ordered basis. So with respect to standard ordered basis, the matrix representation of T is given in matrix A. Okay. For both domain and the codomain, based on this information, answer the subsequent question. Choose the correct definition for T. So see here that A is 2, 1, 1, 3, 0, 3, minus 1, minus 1, 0. Okay. So you can write this as what can you write this as? You can this in equation form, this will be 2x plus 3y minus z x minus, because this is the x component, this is the y component, this is the z component. So the first row can be written like this, the second row can be written like this, and the third row can be written like this. Okay, hence the first option is your representation of t. Txyz can be written as this. Now we go to the next part. The next part says that if B is the matrix representation of T with respect to the ordered basis, so we have given the ordered basis as this, and we have to find the rank of B. To find the rank of B, first we have to calculate the matrix B, right? So we have just found the transformation here. This is the transformation, and we are going to apply this transformation to the elements of basis for the matrix B. For this basis, we are going to apply the transformation, right? T x y z is equal to 2x plus 3y minus z x minus z x plus 3y. Now t t of 0 1 0 t of 0 0 1. Yeah, just a second. Just give me 2 minutes. Okay. Yeah. We are going to apply this 100. Okay. Okay, cool. So what are we going to do here? We are going to apply the transformation to the elements of the basis for the that we have given here. Okay, we are going to apply transformation to this. And we are going to get minus 5, minus 1, minus 4. Like you can check the calculation. 2 into minus 1 is minus 2, minus 3, so minus 5. Then x minus z, this is minus 1, x plus 3y, and then you have to do a into minus 1, minus 1, 0, plus b into 0, minus 2, 3, plus right. I think I did something wrong here or what. Zero, zero. Okay, no, fine. So this is then 1, 3, 1, right? Similarly, apply transformation to this particular, and you get minus 9, minus 3, minus 6, and and you get the matrix B, and from the matrix B you apply like row operation, and applying row operation you're going to get rank as 2. You should get rank as 2. What doubt you have? Week 4, which is basis for vector space. Basis for, okay, so you have doubt on basis of vector space. So suppose you have a vector space. So what is vector space? Basically, vector space is a set of vectors with operation addition and scalar multiplication, and there is a field. Usually the field is R. The scalars are taken from here, and the vector addition and scalar multiplication, they both satisfy certain conditions. Then what is the basis for the vector space? The basis for vector space is it is a set of linearly independent vectors that spans the entire vector space. So the set of vectors which are linearly independent and which also spans, what does span mean? Span means that it like the dimension of the entire vector space is covered by that particular set. So if you take any vector from the vector space, that vector can be written as linear combination, like any vector from the vector space can be written as linear combination of the elements of the basis, right? So that means, so when that happens, then it spans the vector space and linearly independent. When these two conditions are satisfied by any set, then that set is called the basis for the vector space, and the basis for vector space is not unique. Okay, a vector there a vector space can have more than one basis. Okay, so determinant of B. Okay, so this is related to the previous question actually. So in the previous question, when you calculate, you will find the rank is coming out as 2, and if the rank is coming out as 2, it means then there is a linearly dependent row or column, right? So if there is linearly dependent row or column, then determinant will come out as 0, because it contains, because its rank is less than 3, which is why the determinant and B is a 3 by 3 matrix with rank less than 3, and that's why its determinant is coming out as 0. Right, now moving on to the next question. So we have this particular function here, fxy is equal to 1 by x square plus y square, where xy belongs to D. Then D is, where D is the subset of R2, and f is a function from D to R. Okay, so now we have to say which of the following is the largest possible set that would be valid domain D for the given function f. So we have a function f and we have to find the domain of this particular function. So notice that if x is 0 and y is 0, then f will not be defined. So for f to be defined, we need to have x square plus y square non-zero. The denominator has to be non-zero for the function to be defined, and hence this is our option, which is the domain of this function. This is the correct option. The next is
Ma'am, can
that,
you repeat it once again?
yeah, sure, of course. Um, the function is fxy is equal to 1 by x square plus y square. Now notice that if the denominator becomes 0, so if x square plus y square, if x square plus y square becomes 0, then f is not defined. It can't be defined for x square plus y square is equal to 0, which is why we need to have x square plus y square is not equal to 0 for f to be defined. When we are saying that some set is domain of a function, then the function has to be defined in that particular set. Okay, is that clear?
Yes, ma'am.
Okay, so hence the second option is our the correct domain for the function f. Now we have a domain given to us, uh, domain such that x square plus y square is less than half, and for this domain we have to say what is the range of f, right? So if x square plus y square is less than half and we cross multiply it, what do we get? We get 2 less than 1 by x square plus y square, which means fxy should be greater than 2, right? That should be the range. So
2
fxy
to
greater than
infinity.
2 to infinity, the third option. Next we have that which of the following choices the function f is injective. So injective is the condition. So I'll break it down for single valued and then for multi-valued. So what is injective? So when we have a function fx1 is equal to fx2 implies x1 equal to x2. This is the condition for injective for single valued. And when we have multi-valued, f of x1 y1 is equal to f of x2 y2, then it should imply that x1 is equal to x2 and y1 is equal to y2. So when this condition is satisfied, then we say that the function is injective. Okay. What's the function we have? We have fxy is equal to 1 by x square plus y square, and we have to check if this function is injective or not. So basically, if it is injective, then what should be the domain? The choices of D, where the function is injective. So let's first check the condition of injectivity. This means that just straightforward, I only applied the formula for fxy. Where on the definition of injectivity. Uh, when will this be equal? When x1 square is equal to x2 square and y1 square is equal to y2 square. Now for squares we know that 3 square is 9 minus 3 square is also 9, but 3 is not equal to minus 3, right? Here
Yes, ma'am.
we have the condition that x1 square is equal to x2 square, which means if we take some positive set, then it is going to be true always, right? If the value contains both positive and negative numbers, then the condition may also be false, as we see in this particular example. So we have to check in which domains the values of x and y are positive. So let's check the options now. Uh, okay. So what do we have here? We have that 0y, y greater than 0. Okay. So y is positive here. In the second option, y is negative. So this is the wrong option. Y cannot be negative. Again 1y less than 1, y again cannot be negative, because if y is negative, then the y1 square equal to y2 square will not give us y1 equal to y2. So this also is the wrong option. So our correct options are this and this, because in these two cases y is non-zero. Okay, this is also false. This is also false because the negative values of y will give same results, right? So the first option is the correct option. uh okay, so now we have the last question for today. um, Let f be a function from R2 to R, be the function defined as follows: fxy is equal to x to the power m y sine 1 by x if x is not equal to 0, and k if x is equal to 0, where k is a real number and m is a positive integer. So we find the value of k for which f is continuous at 0, 0. Okay, we have to find this value where it is continuous. So we have to examine the function first. So let's look at the function. The function f is from R2 to R, and fxy is given as xmy sine 1 by x for x non-zero, and k for x 0, and where we have to check for continuity 0, 0. This is the point where we have to check for continuity. So notice that sine 1 by x is a bounded function. Why do we say that? Because we have seen the value of the graph of sine is like this, right? The value is always between 1 and minus 1. So this is the like any this is not the graph of sine 1 by x. Sine 1 by x will look a bit different, but what I mean to say is the value of sine is always between minus 1 and 1, no matter what value is. Okay, so I'll not confuse, I'll not say that this is sine 1 by x का graph ऐसा नहीं होता, but the value of sine is always between minus 1 and 1. uh, right? So f of xy will always be between like mod of fxy is less equal to mod of x to the power my. To find like the value of k for which f is continuous at 0, 0, to find that value, uh, we can take limit xy tends to 0, 0 mod of xmy, and if we take y is equal to x, then we'll see that limit xy tends to 0, 0, this will be 0. When we take this, we can examine it for other directions as well. Say we take y is equal to sine x, then what happens? Then fxy becomes what is the function? So fxy becomes xm sine x sine 1 by x. So these two again, the value is between -1 and 1, and we are reducing the value of x. Why we are reducing? Because x is tending to 0, and hence as xy tends to 0, 0, we see that fxy tends to 0. Okay. Now we want the value to be continuous. When is it continuous? It is continuous when the value of the limit comes out as equal to. So if the if fxy tends to 0, 0 gives fx tends to 0. As xy tends to 0, 0, we have f of xy tends to 0. And for x equal to 0, the value is given as k. If this value becomes equal to this value, then we will have
0.
continuous. So k equal to 0. So for k equal to 0, the value will come as continuous. Okay, so I'll stop here. We have covered most of the topics from matrix transformation, domain, um continuity, the partial derivative part. So most of the weeks are covered in the questions that we have discussed. If you have any doubts anywhere, you can ask. Yes, I can share the PDF. Sure. Uh, the video will be uploaded by the house. Okay, the video will be uploaded by the house. Projection. Right. So okay, so projection was actually discussed when I took another session before this. The link can be shared. Yes, link can be shared. Yeah, anything else? Okay, then I'll stop the recording. Yeah, okay, all the best.